So I have 2 hours, right? Okay. So I'm going to be a little bit more mathematical and talk about an algorithm for efficient learning from high-dimensional big data. And this is a joint work with Tong Zhang. So just a quick reminder, what is machine learning in its most simple form. Our goal is to learn the predictor, which is a mapping from some domain X, for example, images, to some domain Y, for example, a set of predefined categories. And to do so, to learn this function, this is maybe the artificial intelligence or what are we looking for. We have at our disposal training examples, which are just pairs, x1, y1 to xn, yn. N is a number of examples. Each such pair is, in this example, an image and the true category to which the image belongs to. So we have this training set, and we want to find a good learning rule. So one common approach, which at least in the past was very, very popular, until today it is still highly used in practice, is the following. So first we represent objects as some high-dimensional vectors in dimension D. For example, think about text documents. So you can think about a representation as n-grams. So each sequence of n words becomes one feature. The number of features is all possible number of n-grams, which is huge. And another example is images represented by some visual words. Then we learn a linear predictor, so we learn weights over the d-dimensional representation of the object, and this forms our predictor. Based on this linear function, we get our decision. So this is a big data problem because both the number of examples n can be very large or should be very large. If we want to learn high-dimensional objects, we also need a lot of examples. And the dimensionality, D, is the number of words that represents our object, is also very, very large. So now what we do, we want to find this linear prediction, and there are many ways to do this, but most of them relies on a particular form of an optimization problem, which we call regularized loss minimization, which I will define in the next slide. I just want to mention that the many machine learning paradigms fall into this optimization, boils down into this optimization problem. For example, ridge regression, logistic regression, Lasso, linear SVMs, and more. Okay, so this is a very common thing to do in machine learning. So how this regularized loss minimization, or RLM for short, optimization problem looks like. Our goal is to find a vector W, which lies in RD. So it's a d-dimensional vector. Remember that D is very, very large. And it should minimize an objective function P of W, which comprised of 2 parts. The first part is an average of a composition of some function phi. Phi is a scalar function over a linear function, which is just the inner product between the vector W and xi. Xi is a representation of our object as a d-dimensional vector. So we take many such vectors. We apply the linear function. We apply this nonlinear, possibly nonlinear function phi, and then we average all of this. This is the last part of the optimization problem. The other part is a regularization function, R of W, which comes together with a regularization parameter lambda. Okay, so let me give a concrete example, which is the simplest example, ridge regression. So in ridge regression, our examples come with labels yi, which are just scalar. So we take the inner product between w and xi, which is a scalar. We subtract yi, and then we take square. So this forms the loss part, and the regularization part is simply the squared of the Euclidean norm. Okay, so we have this type of optimization problems. And in this talk, I will focus on each phi being convex and smooth. I will later mention non-smooth loss functions as well. And the regularization R should be strongly convex. And both D and M are very, very large. Okay? So this talk is about how to solve efficiently this optimization problem. Okay? Or such optimization problems. Okay, so let's think about the common approaches to solving this problem. So we would be very happy with an approximate solution. So we want to ask how much time requires to find a solution W such that P of W minus P of W star is the optimal solution, is smaller than epsilon. So one popular option is Newton method. Now, if we go back for a moment to the ridge regression problem, if you take the derivative of the objective for ridge regression, you obtain just solving a set of linear equations. And the linear equations, to form this set of linear equations, you need d squared times n just to calculate the matrix. And then you need d cubic to invert it. Once you do it, you have an exact solution. Newton method does something very, very similar, but in the general case, at a smaller cost, at a small cost of multiplying this runtime by log 1 over epsilon, which is very, very, very small. Okay? So this is one approach to solving the regularized loss minimization. Another approach, which is called the first order method, is gradient descent. And I will explain what is gradient descent later. Gradient descent for this problem, this type of problem, costs d times n. Again, d is a dimension, n is the number of examples. Now we have also 1 over lambda. If you forgot, lambda is a regularization parameter. It actually tells you how much curvature you have in the objective. And then we have log 1 over epsilon. Okay, so this is gradient descent. Now there is a new, relatively new method called accelerated gradient descent, in which 1 over lambda is improved to 1 over square root of lambda. And then there is something much simpler, which called stochastic gradient descent. And the runtime of stochastic gradient descent for this problem is d over lambda epsilon. I will elaborate on stochastic gradient descent and gradient descent later. But just by looking at all of these numbers, which method is the best? The last one is the best. Why? Because it doesn't depend on n at all. Okay? On the other hand, the last one depends on 1 over epsilon, while accelerated gradient descent depends on log 1 over epsilon, and Newton method maybe depends on log 1 over epsilon. So Newton method is the best in its dependence on 1 over epsilon. And stochastic gradient descent is the worst in its dependence on 1 over epsilon. On the other hand, the other parameters, the last one is the best. Okay?
But there's no lambda, you just not comparable, right?
Sorry?
There's no lambda, you're doing the unregularized.
There is no lambda in Newton method? Yeah. Yeah, there is a very, very tiny dependence on lambda, if at all, for Newton method. Yeah, sure. Okay. So, so we need to find a method to understand which method is better than other method, and maybe there is even other method which is better than all of these methods. And this is, of course, depends on the specific problems that we are aiming to solve and what is an interesting regime for our problems. So let's talk about the type of problems that we are trying to solve. So first, it was mentioned before, data. This training set is sampled from some statistical source. So in any case, we have sampling noise in the creation of the training set. So there is no sense really, there is no really sense to optimize very, very accurately. And typically in applications, taking epsilon to be 10 to the minus 3 is more than enough. On the other hand, D and N, both of them are very, very large. So runtime that depends on n d squared, like in Newton method, is not reasonable because this will take forever. Another aspect of such problem is that data is usually sparse, meaning that for every xi, most of the elements of xi are 0, and just few of them are non-zero. And also, for statistical reason, in many cases, lambda should be order of 1 over n. Okay, so once we take all these considerations and take maybe a typical example, so I take an example of say 10 millions of examples. The dimension is millions, and the effective dimension d sub e is 100. This is typical in text processing problems. Let us take lambda to be 1 over n and epsilon to be 10 to the minus 3. And then when you work out the numbers, you see that Newton, which is maybe the best method from optimization point of view, because it depends on log 1 over epsilon, is a worse method for this regime. Gradient descent is better. Accelerated gradient descent is even better. But then stochastic gradient descent for this regime is the best method. OK, so what I'm going to present is a new algorithm, which is called accelerated stochastic dual coordinate ascent. And this new algorithm is significantly better than all known first-order methods in the relevant regime, such as the typical examples that I mentioned before. So I'll try to explain how it improves over stochastic gradient descent, why stochastic gradient descent is good, how the new algorithm improves over it, and what is the new analysis or the rate of the algorithms that I will present. OK. So just to give you a little bit heads on. So on the typical examples that I showed before, if stochastic gradient descent is 10 to the power of 12, and this was the best so far, the new algorithm will be 3 order of magnitude faster than stochastic gradient descent. Okay, so it gives a significant improvement. Okay, so to explain the new algorithm, I first want to recall what is gradient descent, what is stochastic gradient descent, and why stochastic gradient descent is better than gradient descent in this regime, and what's wrong with stochastic gradient descent. Okay, so let's recall the optimization problem. We have an average of simple functions, of n simple functions, plus regularization term. Applying gradient descent is a very simple algorithm. It's an iterative algorithm. We start with some initial value of w, and then we update w based on the gradient of the objective. So what is the gradient of the objective? Simple thing to see is that the gradient of the loss part is average of the individual gradients for each phi I, which I denote by phi prime I. And the gradient of the regularization part is simply lambda times w. So we take our w and we subtract the gradient with some scalar eta t that can change along the optimization process. So this is a very well-known algorithm, gradient descent. Stochastic gradient descent makes the observation that instead of taking the exact gradient of the loss part, we can actually take an unbiased estimate of this part. And just by taking a single I uniformly at random and taking the gradient just of the function phi I, we obtained some vector which is an unbiased estimate of the original gradient. And then we just make a step along this direction. So if we take a simple quadratic function and look at these two algorithms, so what we can see is that gradient descent goes nicely to the optimum, to the minimum of the function, and stochastic gradient descent looks like I drive at the evening, okay, after drinking a few. Never mind. Okay, so. So what we can see here is that at the beginning of the process, when we start to optimize, it actually makes a lot of sense to do stochastic gradient descent, because we sort of go to the right place, and we're far enough from the optimum, so it doesn't really matter if we do exact steps according to the gradient or approximate steps according to the gradient. We actually go to the to the right region in any way. But at the end of the optimization problem, gradient descent is very, very good, while stochastic gradient descent continues to do some crazy things. And mathematically, this translates to 1 over epsilon dependence for stochastic gradient descent versus log 1 over epsilon dependence for gradient descent. So the variance hurts when we are close to the optimum. Now, you might think maybe there is a clever way to circumvent this problem. So this theorem tells you that, that you need to change something more deeply if you want stochastic gradient descent to be good. So the theorem says that any algorithm for solving RLM that only accesses the objective using stochastic gradient oracle. So I look at a family of algorithms that access the objective just by asking for a stochastic gradient. Okay, so all of these algorithms, if they have log 1 over epsilon rates, then they must perform n square iterations, meaning that they will be very, very slow. Okay? And the proof is based on a very simple observation. Just look at 2 objectives, which are part of the regularization minimization framework. In both of them, you can think about, I have almost exactly number of examples, both of them just in one-dimensional. Okay, all the positive examples are here, or half of the positive examples are here, half of the negative examples are here, and now I have one more example, which I can put either here or here. Okay? So this is 2 objectives. Either I put the extra example here or here. Both of them are very, very similar. Now, if you access this objective using a stochastic gradient, what you will get is exactly the same information as you flip a coin whose bias is exactly half, 1/2 plus 1 plus minus 1 over 2n, and plus or minus depends if we are in case 1 or in case 2. Which means that if the only thing, Sham, I will get back to you soon. So if we only have access to stochastic gradient oracle, then we cannot do anything better than determining the bias of the coin, which we know that takes n squared time. So if an algorithm manages to optimize very, very good these objectives, it must make n square iterations. If you want to.
This seems a bit of an issue. Can't you do like a random rotation and break this? And like the random hierarchies are cheap.
But okay, but this will not be a stochastic gradient oracle. So if you have another access to the objective.
Yeah,
so
that's right. But it's access to like the same problem but rotated.
Yeah, but you know it's a question of order of quantifier, because for any random rotation there will be such problem. So the question is, first you do random rotation to the data, and then that's right. What I'm going to suggest is something even simpler. Okay, I'm going to change the oracle, the way we access the data. Okay. Okay, so our approach, we see that we need a stronger oracle access to the data. Sham was suggesting first doing some random rotation and only then, but maybe this is good, but this is not our solution. What we want, we don't really care about stochastic gradient. We know the objective. The only reason we do stochastic gradient descent is because we want cheap iterations. Okay, there is no information limit here. There is just our will to have a very, very cheap iteration. So we want another stronger oracle access to the data. We want each iteration to be cheap, and we need to solve the problem. To solve the problem that when we approach the minimum, we want the variance to be controlled in a smart way. So our solution is based on a primal dual approach. And for this, I need to give you just one definition from duality. In particular, the concept of Fenkel duality or Fenkel conjugacy. And the idea here is very, very simple. If you have a function, you can represent it by one of two ways. One way is a set of points, which is a usual way that we look at functions. This is the blue representation on your left. Another way is just to say the set of all tangents of the functions, which, as you can see, also gives you the same information. Okay, so what we can say is that we can represent the function as w and the value of f of w, or we can represent it as a slope of a tangent theta, and then where this tangent intersects the y-axis, which is minus f star of theta. Okay, so the function f star of theta that do this mapping from f to f star is called the Frenkel conjugate function. Okay. Now, based on this function, we can write a dual problem to the original problem. So on the top, you can see the original problem. Again, we have average of functions plus regularization. And on the bottom, you see the dual problem. The dual problem, the variables of the dual problem is alpha, which is a vector in n dimensions, meaning that we have a single dual variable per training example. Okay? And then we have, again, an average of dual functions minus some, again, square norm, but now the square norm is for linear combination of the examples using the weights alpha I. Now, what's nice about the dual problem, which I will write on the top, again, is that we have the composability of the dual problem per variables. So if you look at the average of phi star I works over minus alpha I, you see that each dual function, phi star I, works only on a single dual variable. Okay? So this part, the first summand in the dual objective, is decomposable into different variables. The only coupling of variables happens at the second term, and there the coupling is very, very simple. It's just take a linear sum of examples using weights alpha I and takes a square norm of it. So this form is very, very convenient for optimization. The idea of dual coordinate descent is simply to, at each iteration, to fix all the dual variables but one, and to optimize over one variable. And stochastic dual coordinate descent is exactly the same, just we pick uniformly at random which dual coordinate we want to optimize over. And because of the structure of the dual problem, the per iteration runtime of a single dual coordinate ascent iteration is the same as stochastic gradient descent. By just keeping track of these sums, 1 over lambda n sum alpha I xi, if we keep track of it, we can update one variables at the cost of a single inner product in d dimension. So the cost is exactly like the cost of stochastic gradient descent. So we lose nothing by accessing the function differently. But let's see what we gained. So first, experimental observation. So this is on a text processing data set with almost a million examples, 10,000 dimensions. What you see in the black line is stochastic gradient descent. What you see in the y-axis is the accuracy. How far are you from the optimum? It's in logarithmic scale. Okay. What you see in the x-axis is how many iterations measured by how many epochs over the data, how many times you go over the entire data set. And what you can see is that SGD is very slow, while in stochastic dual coordinate descent, you see almost a straight line, which means that the convergence rate is logarithmic in 1 over epsilon, as opposed to 1 over epsilon for stochastic gradient descent. So a straight line in semi-logarithmic scale, meaning log 1 over epsilon dependence. There is another two variants here. One is in one we choose dual coordinates with repetitions or without repetitions. So this is the only difference. Okay, so we see that this algorithm works very nice in practice. Actually, it's not a new algorithm. This idea is not new. It is well known, and it is actually even implemented in software packages. But the analysis of this algorithm was not satisfactory. So there was analysis of 1 over lambda epsilon square, which is worse than SGD. Of course, it doesn't tell us the story. There was another analysis which shows a rate of log 1 over epsilon, but there is some constant 1 over nu, but this constant can goes to 0. So this is also not a satisfactory analysis. And our result is that the number of iterations that you need to do is n plus 1 over lambda times log 1 over epsilon. So we have a crisp characterization of how the number of iterations depends on all the parameters of the problem. Now, the previous analysis of Lu and Tseng that I mentioned here, that has 1 over nu times log 1 over epsilon, works no matter how you choose which dual coordinate to update at each round. So you can do round-robin choice of parameters. And what you can see in this graph is that if you do round-robin cyclic order over examples, then the performance is much worse. And in fact, it is worse than our bound. And the way I found out about this fact is just by making a bug in my implementation of stochastic dual coordinate descent. So what I did, I wanted to see how it works in practice, and I implemented it, and I saw the black line. But I knew that I had the red line as an upper bound, so I thought, oh, either I had a bug in the implementation, or I have some bug in the theoretical analysis. And then I checked the code, and the code seemed to be correct. And I checked the analysis also seemed to be correct. So what was the problem? And then I found out that what I did incorrect in the implementation is that I chose a random permutation over the examples once, and then I started going again and again, not too many times. You see there is maybe 10 passes here or 18 passes over the data again and again using the same order. Now, this is very strange because the number of examples here is maybe 1 million examples. So somehow, this algorithm has memory and remembers one particular order over 1 million of examples, but the algorithm does very...
So what's the dimension?
The dimension here is 10,000. So high dimension, many number of examples, millions of examples, 10,000 dimension, and somehow it's still very strange that the algorithm remembers a particular order that I went through the examples, and then in the second pass it becomes worse and worse because of this memory. Okay? And if you do just random permutation at each epoch again and again, it works great. So this was a bug, which is still very strange that this is a bug. But okay. Now after and in parallel to our work, there are other variants of SGD that also achieve this rate of d plus 1 over lambda log 1 over epsilon. Okay. So what I want to do is first show you two simple reductions that enable to use it not just with squared norm regularization and not just with smooth functions. And then I will go to the next layer of our algorithm, which is the acceleration part. Okay, so suppose you want to use this algorithm for L1 regularization rather than L2 regularization, just as an example. What you can do is add a slight L2 regularization, and everything works, and you can prove that if you add order of epsilon L2 regularization, then everything, then solving the regularized problem is the same as the original problem. For L1 regularization, it gives soft thresholding. The algorithm is still very, very simple. So this is one type of reduction. The other type of reduction is if you have a Lipschitz loss and not a smooth loss, then you can just smooth it, and you can prove that this smoothing will not affect the objective too much. And we have a general mechanism to do this, but in picture it looks very simple. It just take a non-smooth loss and just smooth it. Okay, so this is just to mention that the applicability of this algorithm is not just for smooth and L2 regularization. It works for many other problems as well. Let me, okay, maybe I should say a few words about it. So what we found empirically is that, for example, if those of you that like the hinge loss function, which is used in support vector machines, if you smooth the hinge loss and use a smooth version of the hinge loss, nothing really happens in terms of performance in the accuracy of the 0-1 error. So what you see here is sometimes the performance is worse, sometimes it's better, sometimes it's in the middle, but the scale in all of these y-axis is below the statistical significance, so it means that it just not really matter. In terms of runtime, it actually helps you a lot. So this is just something to keep in mind. Anyway, let's continue to the acceleration part. Okay, so Nesterov came out with a very nice idea, which is called accelerated gradient descent. And the idea is just in terms of doing a gradient descent, just using one gradient at a time. Let's remember also the previous gradient and use two gradients to update our weight vector, our solution W, and you gain from it. You don't lose a lot. You maybe lose a factor 2 in terms of the cost of each iteration, but you gain a lot in the number of iteration requires. And the gain is, instead of a dependence on 1 over lambda, where lambda is a regularization parameter, now the dependence is on 1 over square root of lambda. Okay? Now, the stochastic dual coordinate ascent algorithm that I showed you before, the runtime of this algorithm is n plus 1 over lambda. So gradient descent is n times 1 over lambda. Accelerated gradient descent is n times 1 over square root of lambda. And stochastic dual coordinate ascent is n plus 1 over lambda. Okay, so now if you compare accelerated gradient descent and SDCA, it's not comparable. It depends on the relationship between lambda and n. Okay, if lambda is very, very small, then accelerated gradient descent will be better than stochastic dual coordinate descent. So the natural question is, maybe we can do the same trick. Maybe we can accelerate stochastic dual coordinate descent. Okay, so it's not a trivial thing to do, because the way accelerated gradient descent is presented is usually tailored very, very heavily to deterministic algorithms, while we have stochastic algorithms. But there is a way to do it. And the way to do it is to think about an algorithm which has several calls to stochastic dual coordinate ascent as a black box. And the only difference is that whenever we call stochastic dual coordinate ascent, instead of calling it with the original P of W, we add a little bit regularization around some vector which depends on where we are. Okay? So it looks ugly, and I deliberately wrote everything, but all these parameters are actually not parameters. There are things that you don't need to set them. They are set automatically. So there is kappa, which is set automatically by conditions of the problem, which you can calculate and you can easily calculate. So I wrote it ugly, but I want to mention that it's very simple to implement. And then the heart of the algorithm is just, so you maintain y and w. There is a simple equation to update y. And then you call SDCA on P tilde of w, which is exactly P of w plus regularization parameter kappa. And you regularize around the previous y. This is it. Okay? So it's quite easy. So what we can prove? So the runtime of accelerated stochastic dual coordinate descent. Now we have n plus square root of n over lambda. So in SDCA, we had 1 over lambda, so it's better than SDCA in all cases. Sorry, not in all cases. But what we actually have is a minimum between SDCA and accelerated SDCA, which is better than accelerated gradient descent in all of the cases. Okay? So we ended up with a dependence on n plus square root n over lambda for small lambda, or n plus 1 over lambda for large lambda. Okay, let me skip the proof and just show you some evaluation on 3 standard data sets where we used this method to solve an L1, L2 regularized problem. So the 3 graphs are for 3 different data sets. And what you see is 3 algorithms, SDCA and ASDCA that I described. FISTA is a version of accelerated gradient descent. FISTA is a version of accelerated gradient descent for L1, L2 regularization. So what I'm going to show is the situation where lambda is not very small and the situation when lambda is very small. So lambda of 10 to the minus 7 is not very small. In this lambda, even SDCA is better than FISTA, as you can see. And accelerated SDCA is much, much better. And in fact, what you can see that in all of these data sets, very few passes over the data gives you a very accurate solution to the optimization problem, except the astrophysics data set, the leftmost one, which is very small in terms of the number of examples. So it's not surprising that we need few more passes over the data. Now, when lambda becomes very, very small, SDCA starts to behave strangely. It will converge at the end, but at the beginning, it has a dependence on 1 over lambda, so it will take it some time. FISTA becomes better relatively to SDCA, but the acceleration part still behaves roughly the same and converges very, very fast relatively to the other methods. Okay, so this workshop is about big data. And I presented an algorithm for big data, but not very big data. Okay? Because here I assume that, that the data that you work on can be fitted into the memory of one machine. Okay? But what about data that cannot fit into the memory of more than one machine? Okay, so then you want to parallelize. So if you want to parallelize on a shared memory machine or virtual shared memory machine, this is very, very simple to do with accelerated stochastic dual coordinate descent because you can simply accelerate the inner product. So if you have GPU, you can accelerate the inner product. If you want to accelerate more, you can work with mini batches, and we have also an analysis for this. So it's also very, very easy to accelerate on a shared memory machine. What about MapReduce or things that do not fit into the memory of a single machine? So Nati Srebro and Ohad Shamir and Tong Zhang has a very new interesting paper about solving few problems, each of which you can solve using SDCA and then combine the results. Still, it's an active research topic. The analysis is not satisfactory. I actually don't know what's the actual performance of these algorithms. And it's not clear at all that a simple hot potato approach where you just solve the problem on one machine and then pass the solution and solve from this solution on another machine will not work better than all the more sophisticated methods. Yet to be seen. Anyway, let me just wrap up. So SDCA is a very, very good algorithm. It has properties of stochastic gradient descent that has very cheap single iterations, but it controls nicely the variance towards the optimum. And we presented also an acceleration of SDCA, which, to the best of my knowledge, is the best method nowadays for first-order methods. There are many open questions. First, we still don't know if this is optimal. Maybe you can do even better. How to do non-trivial parallelization. What about being adaptive to the geometric of the specific data that you have? What about loss functions that are hard to be smoothed, like what people have in structured output problems? And of course, what about non-convex losses, neural nets, and all that? Okay, thank you very much.